MS Ramaiah University of Applied Sciences.
Hi students, let us have the discussion on major and minor losses. Aim of this experiment is to determine the head loss due to friction for flow through pipes and identify the flow regime, that is either laminar or turbulent flow. Experiment also aims at determining the head loss in flow through pipes due to various pipe fittings and the loss coefficient. During fluid flow, there exists a velocity gradient. Hence, shear stresses are produced in the whole liquid due to viscosity. Liquids flowing through pipes are encountered with resistance resulting in loss of head or energy of liquids. This resistance is of two types, depending upon the velocity of flow, viscous resistance and frictional resistance. Resistance between two different layers of a fluid caused by intermolecular interaction between molecules of the fluid is called as viscous resistance. And the resistance due to the friction between the fluid and surface of the pipe is called the frictional resistance. Head loss of the fluid is significantly more when frictional resistance predominates over viscous resistance. Here we can see the difference between the viscous resistance and the frictional resistance. For viscous resistance, the red line indicates the resistance between different fluid layers, and for frictional resistance, the red line indicates the friction between fluid and pipe surface. We shall find the head loss due to friction using Bernoulli's principle. The principle states that for a steady, inviscid, frictionless and incompressible fluid, the algebraic sum of pressure head, kinetic head and potential head remains a constant between 2 points in a fluid flow. It can be stated that P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2. In practice, total head at 2 is always less than the total head at 1. This is because of the friction present between the fluid and the pipe. The loss of head due to the friction is termed as head loss, represented by HF. Friction factor is a dimensionless constant which relates the head loss due to friction to the velocity or flow rate of the fluid. Darcy friction factor or Darcy-Weisbach friction factor can be expressed as Fd is equal to Hf into 2g into d divided by L into V square, where Fd is the Darcy friction factor, which is a constant. Hf is a head loss due to friction in meters of water. G is the acceleration due to gravity, that is 9.81 meter per second square. D is the diameter of the pipe in meters. L is the length of the pipe in meters, and V is the velocity of the fluid in the pipe in meters per second. The other friction coefficients that are popularly used are the Manning constant, N, and Chezy constant, C. These constants are mainly used for open channel flows. Reynolds number signifies the predominance of inertia forces over viscous forces, or in other words, the ratio of frictional resistance over viscous resistance. Higher Reynolds number indicates more turbulence that leads to higher losses due to frictional resistance. Reynolds number is expressed as Re is equal to rho Vd divided by mu, where rho is the fluid density in kg per meter cube, V is the velocity of the fluid in meter per second, and d is the diameter of the pipe in meters. For a fluid flow in a closed conduit, if the Reynolds number is less than 2300, it is termed as laminar flow. If the Reynolds number is more than 4000, it is termed as turbulent flow, and the value between 2300 to 4000 is called as transition flow. In this image, we can observe the different flow regimes of laminar, transition and turbulent flows. For different diameters of the pipe, it can be expected to have higher head loss due to friction for larger diameters. Also, at higher velocities of the fluid or at higher values of Reynolds number, the head loss also can be expected to increase. Friction factor gives a direct indication of the head loss that occurs in a closed conduit. With more number of experiments on a particular pipe or conduit, a generalized acceptable friction factor can be derived. Hence, in designing a pipeline, based on allowable pressure drop or head loss, appropriate pipe can be selected if the value of friction factors are known. While we have discussed head loss due to friction between pipe surface and fluid, it should also be noted that head losses can occur due to pipe fittings, bends, etc. present on a pipeline. In a pipe flow having span of the pipe significantly long, the losses due to the pipe fittings is very much small when compared to the losses due to friction between the fluid and the pipe. Hence, losses due to the pipe fittings is also called as minor losses. Pipe fittings induce change in direction of fluid flow, which creates turbulence and reversed flow. At Ramaiah University of Applied Sciences Laboratory, we have installed 3 different types of valves that are commonly used for domestic and industrial purposes, that are non-return valve, wheel valve and gate valves. Among them, it can be expected to have highest head loss across a non-return valve compared to other valves. It should also be noted that pipe bends are very common on a pipeline. And due to this reason, it is important to know the head loss across different pipe bends also. Short bends have sudden change in direction of flow compared to long bends. In pipe bends, the fluid may not follow the contour of the pipe during change of direction. Outer layers of fluid escapes and reversed flow occurs, because of which turbulence is created. Smoother the change in direction, lower is the head loss. Expected head losses in decreasing order are 135 degree short bend, 90 degree short bend, 90 degree long bend and 45 degree long bends. A simple CFD simulation of 90 degree long bend, 90 degree short bend and 135 degree short bends are shown here. Images depict velocities inside the pipe where red color indicates maximum value and blue color indicates minimum. It can be observed that sudden change in pipe contour generates more turbulence. Hence, more head loss is expected in shorter bends. There are also conditions where the diameters of the pipe suddenly change in a pipe flow. For this purpose, a sudden contraction of a pipe from 27 mm diameter to a 15 mm diameter is installed. In this condition, the fluid quickly follows the contracted diameter of the pipe. Head loss is less and turbulence is created only in the region of vena contracta. A sudden expansion of the pipe from 15 mm to 27 mm is also installed. Here, the fluid cannot easily follow the expanded diameter of the pipe. Head loss is more and hence scope to generate turbulence and reverse flow is high. A CFD simulation for sudden contraction and expansion are shown here. The images depict velocities inside the pipe where red color indicates maximum value and blue color indicates minimum. In the expanded view, it can be observed that more turbulence is caused in sudden expansion, hence more head loss is expected in sudden expansion compared to sudden contraction. Based on Bernoulli's principle, the loss coefficient for various pipe fittings can be formulated. Loss coefficient of a pipe fitting gives an indication of how much head loss can be expected from the pipe fitting, represented by K. For pipe bends and walls, K is equal to HF into 2G divided by V square. For sudden contraction, K is equal to HF into 2G divided by 0.5 V2 square. And for sudden expansion, K is equal to HF into 2G divided by V1 minus V2 the whole square, where HF is the head loss in the pipe fitting in meters of water. V1 is the velocity of the fluid in the pipe before sudden contraction or expansion in meters per second, and V2 is the velocity of the fluid in the pipe after sudden contraction or expansion in meters per second. Typical values of loss coefficients for various pipe fittings are given in this table for comparison. When the length of the pipe is significantly long, head loss due to the friction between the fluid and the pipe surface, that is, major loss predominates over the losses created due to the presence of pipe fittings. At Ramaiah University of Applied Sciences Laboratory, the experimental setup is of a compact size. The values of minor losses is equivalent to that of major losses. This is because at smaller lengths of pipes, head loss due to friction is also less. To measure the pressure of fully developed flow, the pressure tapping is to be placed ideally at a distance of 8 times the diameter of the pipe from a pipe fitting. Due to compactness, the tappings are placed very near to the pipe fitting. Hence, the flow may not be fully developed, that may lead to values of higher head loss.
Hello everyone. Today we will be conducting an experiment to calculate the head losses through pipes. The head loss through long distance pipes is called as the major loss, and the head loss across pipe fittings is called as the minor loss. Here, this setup is the major and the minor losses setup. This setup consists of a storage tank where the water has been stored. From the storage tank, there is a suction line to a centrifugal pump which shall pump the water from the storage tank to all the pipes. From the downstream of the pump, we have a discharge valve through which we can control the flow rate of the water flowing through the pipes. Further, this pipe is connected to a header from where the water can be distributed to various pipes via different valves. From the header, we can actually allow the water to flow through the long distance pipes. Here we have a 1 inch GI pipe, a 3/4 inch GI pipe and a 1/2 inch GI pipe, such that we can calculate the head losses for various diameters of the pipes. In this setup, the first 3 pipelines, as mentioned before, are for the major losses, which is consisting of various diameters, and the last 2 pipes are to calculate the minor losses across various pipe fittings. On the 4th pipeline, the first minor loss can be calculated for the sudden contraction. Here we can see that the pipe diameter reduces suddenly to a smaller inch diameter. Further, we are having another pipe fitting which is sudden expansion. Here the pipe diameter suddenly increases to a 1 inch diameter. Also, we have a short bend 90-degree pipe fitting. After the short bend 90, further down the pipeline, we have a short bend
135-degree.
This also acts as the minor loss. Further down, we have a long bend
45-degree.
where we can again calculate the minor loss. And then finally, we have a long bend 90-degree, which can again be used to calculate the minor loss across this pipe fitting. In the last pipeline, we have 3 different valves. The first one is the non-return valve, which does not allow the water to flow in the reverse direction. Further, we have a gate valve and a wheel valve, across which the head loss can be calculated. Water from all the pipes gets collected in the collecting tank. Here we have a butterfly valve, which can be either opened or closed. Whenever we need to calculate the discharge across the pipe, we close the butterfly valve and we have a piezometer which will indicate the height of the water collected in the collecting tank. Thereby, we can calculate the actual discharge of the water flowing through the pipe. To calculate the head loss across the pipe, we need to calculate the pressure drop across the pipe. The pressure drop can be calculated using a manometer. This manometer is a differential U-tube manometer, for which the limbs of the manometer are connected to one before the pipe fitting and one after the pipe fitting for the minor loss, and for the major loss it is connected across the length of the pipe. For example, in a wheel valve, the pressure drop across the valve can be calculated by opening these ball valves, such that these pipe tappings are connected to the manometers, and hence the pressure drop across the wheel valve can be calculated using the height recorded from the manometer. Let us now go ahead and conduct the experiment. Before starting the experiment, we need to ensure few things. First, we need to make sure that the discharge valve from the centrifugal pump is always kept in the open condition. And one of the valves in the main header should always be open. We should not start the pump with all the valves in the closed condition. Now I have opened the valve for the first pipeline such that we can calculate the major loss across the pipe of 1 inch diameter. Now, keeping the valves open, we should now switch on the main switch. Once we switch it on, we can see that the red indication is appearing on the panel. Now, the whole setup is ready for starting the pump. By hitting the green button, we shall start the pump. Now the water is flowing through the 1 inch diameter pipe. In order to calculate the head loss across this pipe, we need to measure the pressure drop from this end to the other end of the pipe. In order to calculate the pressure drop, we open the valves, the ball valves connected to the manometer over here, and another ball valve is to be opened at the other end of the 1-inch pipe. Now once the valves are opened, also ensure that the valves of the other pipes and pipe fittings are always remain closed. If any of the valve is opened, then we find an error in the pressure drop measurement. Now let us calculate the pressure drop by measuring the pressure difference in the manometer. At the top of the manometer limbs, we have two valves which are kept open such that if any air bubbles are trapped in the pipe, it can be expelled out. After waiting for about a minute or so, we should simultaneously close the valves and then measure the height on the manometer. Now we can observe that there is a height difference between the two limbs in the manometer. We measure what is the height in this manometer, and this height will be proportional to the pressure drop, which shall give us the indication of the head loss across the pipe. Now the water flowing in the collecting tank has to be made to store inside to calculate the discharge of the water that is flowing through the pipe. For that, we shall close the butterfly valve of the collecting tank. Now, the water in the collecting tank starts to rise, which can be observed on the piezometer. At this moment, we shall start the stopwatch for a particular height. Once the time is noted, we should open the butterfly valve back. This process can be repeated a number of times in order to get a consistent value of the time taken to collect the water in the collecting tank. Now we have calculated the discharge and also measured the pressure difference across the length of the pipe. Using these values, we can calculate what is the head loss across the pipe for this particular flow rate. Now we shall repeat the same experiment for a different flow rate. In order to do that, we shall close the discharge valve by one rotation. Each valve rotation shall reduce the valve opening by close to 30%. The experiment can be repeated for 3 different valve rotations and the data can be compiled. Now we shall move on to the second diameter pipe, that is
3/4 inch.
diameter pipe. For that, we shall go near the header and open
3/4 inch.
diameter pipeline's valve. This is a pipeline for the 1-inch pipe and this is the pipeline for the 3/4 inch pipe. Now to allow the water to flow in the 3/4 inch pipeline, we shall open the valve connecting to the header and close the valve of the 1-inch pipeline. Now the water is being allowed to flow only in the 3/4 inch pipeline. Now, to calculate the head loss across the 3/4 inch pipeline, we shall open the ball valve connected to the manometer at one end of the pipeline, and remember that the ball valve was open for the 1 inch pipeline, which has to be closed now. Now, on the other end, we shall open the valve for the 3/4 inch and close the valve which was previously opened for the 1 inch pipe. Now, the manometer's limbs are connected only to the 3/4 inch pipeline. In order to calculate the pressure drop across the pipeline, first let us close the valves above the manometer limbs. We shall observe the height difference in the manometer. Now, to measure the discharge of the water flowing in this 3/4 inch pipe, we shall close the butterfly valve, and after closing, we shall note down the time taken for a particular height of the water collected in the collecting tank. Thereby, we can calculate the discharge of the water flowing through the pipeline. Using the measurements made by the time and the heights in the manometers, we can calculate the discharge and the head loss across the pipelines. Now, the same experiment can be repeated for the 1/2 inch pipe and also for the pipelines containing the pipe fittings. Now, the valve for the 1/2 inch pipeline is open. In order to calculate the minor losses, that is the head loss across a pipe fitting, we need to open either this or this valves, because all the pipe fittings are present on the 4th and the 5th pipeline. Now, let us open the valve on the 4th pipe and close the valve for the 1/2 inch pipe. On the 4th pipeline, the first pipe fitting we can see is the sudden contraction. Here, to measure the pressure drop across this pipe fitting, we need to open the ball valves which are connected to the manometer. Also, make sure that these valves are all closed for the other pipes and pipe fittings. On the manometer, we shall close the valves on top of the limbs and then measure the height difference on the differential manometer limbs. This height difference will give the pressure drop across the pipe fitting having sudden contraction. Now, we have measured the pressure difference across the sudden contraction of the pipe. Now, the same thing can be repeated for sudden expansion, short bend 90 degree, short bend 45 degrees, long bend 135 degrees and the long bend 90 degrees. We need to make sure that the ball valves connected to the manometers before and after the pipe fitting has to be opened, and the ball valves for all the other pipe fittings and the pipes have to be closed. Thereby, we can calculate the head loss or the pressure loss across each pipe fitting. Now, the water is being collected in the collecting tank. Here, we shall calculate the discharge flowing through the 4th pipeline. The sudden expansion, sudden contraction and the bends are present in the 4th pipeline, whereas the non-return valve, the gate valve and the wheel valve are present in the 5th pipeline. In order to allow the water to flow through these valves, we shall open the final and the 5th pipelines ball valve in the main header and close the valve containing bends and sudden contraction and expansion. On the fifth pipeline, we can see a non-return valve in the beginning. To calculate the pressure drop across this non-return valve, we should open the ball valves before and after the valves which are connected to the manometer limbs, making sure that the ball valves of all the other pipes and pipe fittings are closed, only keeping the non-return valves, ball valves that are connected to the manometer are open. Near the manometer, we shall close the valve. Now we have calculated the pressure drop across the non-return valve, and the same procedure can be repeated for the gate valve and the wheel valve. Now the water flowing in the fifth pipeline is getting collected in the collecting tank. Here we can again close the butterfly valve and then measure the height of the water that is collected, and then also calculate the time required for that particular rise in height of the water. Thereby, the discharge of the water flowing through the pipeline can be calculated. Now, we have calculated all the pressure drops across all the pipes and the pipe fittings, and also measured the time taken for the water to get collected in the collecting tank. After getting the values for the discharge and the head loss, that shall conclude the experiment, and now we shall stop the pump. With the values of head loss and the discharge, we can also calculate the Reynolds number of the water that is flowing through each pipeline. Now with these values, we can plot a graph of head loss against the Reynolds number, and also do the same for different flow rates. That concludes the experiment on the major loss and the minor losses of the water flowing through the pipes.
At MSR UAS, we spark your imagination unlike any other.